Let's go through some answers. What is this one in decimal? 1, 3, 11, 27. Okay, what about this one? All right, what about this one?
341. Does that say 814?
All right, so this is, we have 1 plus 4 plus 16 plus 64 plus 256. So 256 plus 64 is 320. This is 336, 340, 341. Okay, what about the bottom one? 789? Heck yeah.
I'm scared.
Ah, me too. All right, what is the binary on these? Top one.
1, 1, 0, 1, 1, 1, 1.
Yeah? All right, what about this one?
1, 0, 0, 0.
All right, okay. This. All right, let's pick one person.
I got this.
1.
I'm picking Duncan.
Okay, you ready?
All right.
1, 0, 0, 0, 0, 0, 0, 1, 0.
Bless you. All right. Big numbers now. Donut's got this one. Okay, go for it.
1, 0, 1, 1, 1, 1, 0, 0, 0, 1, 1, 1.
Ivana agrees. All right. You want the last one, Garrett?
Yeah, 1, 1, 0, 1, 0, 1, 0, 0, 0, 1.
Allow us to commence. That's let's go back in the 17th century.
Oh, let's go.
Yeah. Allow us to commence. All right, so it's a fun exercise. You need to understand what these are. You need to understand the conversion, but really you're not going to be doing this a whole lot. You can Google these conversions. I know, right? It's an easy, simple bit of programming, but... Oh, wait, oh, darn. Sorry, I actually feel bad. Okay, it's over. Okay, so why is this important? Because math.
Binary numbers is the way to transmit information.
Okay, so there are two ways to get a binary number. All right, way number one is called serial communication. That's what happens when you talk to your Captain Crunch. All right, in serial communication, a digit is transmitted every clock cycle. Okay? So if we draw out a number timeline, and here every one of these ticks represents a clock cycle. then what you would have is every few seconds or so, every few milliseconds or microseconds or nanoseconds, you're transmitting a new digit, okay? And then that's how you would read a number. And so if you're transmitting an 8-digit number, you would have 8 time intervals that it would be required to receive that number. Okay? That's called serial communication. One digit after another with time. Now, this becomes really cumbersome with very large number sets. Okay? If you can only transmit one digit per time, in order to send the number, what, 3041, it would take like something like 10 or 11 time cycles, which that begins to take a finite amount of time. Okay? Right now our best time processors are in the gigahertz range. Gigahertz is 10 to the 9th cycles per second. So you're dealing with a billion, or like 3.5 billion bits that can be transmitted every second, okay? 3.5 billion bits. If you're sending a whole bunch of 3,000, well, 4-digit decimal numbers, you're really limited on how much communication you can actually do. So that's unfortunate. Serial communication, though, it's reliable. But the second way is called parallel communication. Now, you'll notice again, when it comes to this, the base word here is series. The base word here is parallel. You see that a lot in circuits. The idea behind parallel communication is that multiple digits are transmitted, delicious, simultaneously through multiple lines, okay? So here, what you may have is, in your timeline, every time you have a clock cycle, instead of just reading a single digit, you're reading a full word. 10110, 00111, 10001, and so forth and so forth. Okay? So here, parallel communication uses serial communication, and all it does is it allows you to build up more digits, but you're reading a word every time you go to read. Okay? How many of you have ever played a Nintendo 64? A lot of people, actually. Do you know what the 64 stands for in Nintendo 64?
Like 64 bit.
64 bits. You know what 64 bits means?
Like the speed or the power.
64 parallel communication bits being transmitted simultaneously. That's what it means. Every cycle of the clock, you're getting a 64-bit word. Okay? Current operating systems, Windows, operates on a 64-bit operating system. It's because the processor can handle 64 bits at a time. It's weird to think that the same size of processor is being used now as was used in the Nintendo 64 back in 1995. Huh? Well, they've invented things like multi-core processors. They've invented things like, they've increased the speed of the, from a megahertz system to a gigahertz system. So we have increased computing powers, and we've also found ways of improving efficiencies. But this is where we stand. Parallel versus serial communication, okay? So if I have a processor, something that looks like this, and I have Usually what they have is they have a whole bunch of ports here that are soldered, and each of these is connected to a wire, and those wires will go off to certain different components. But here, every one of those wires has the ability to input or output information, giving it the 64-bit processing capability. Okay? So this is a parallel communication device. Parallel communication tends to be a lot more complex because it requires you to send all information, and every single clock cycle, it reads everything. Every one of your components has to exist on that clock cycle, or else if you screw up one digit, it screws up everything. So serial communication tends to be a lot simpler. Parallel communication is far more powerful. It's orders of magnitude here. You have parallel communication with just 2 digits, you have doubled the power of a serial communication system. Every single line you add here is another multiple of how much more information you can bring in. Okay? So, in this class, we're going to be pretty much dealing with just serial communication because that is simpler. We will have some instances where we're using parallel communication, mostly because you have to use parallel communication. What we were talking about in last Thursday's class was an example of parallel communication that only uses 2 digits. Okay, these are a 2-digit parallel communication system, and these are all 4 of the potential states that those 2 digits can be. And then there are derivatives of what happens. And he talked about a state machine using what happens when your 2 parallel communication bits are on or off, or one's on and the other one's off. Okay, the 4 possibilities of what can happen. Now, what I want to leave you with here is, what is the future of computing? There's a simple answer to this. It's Donkin. All right, I'll see you guys on Thursday. That's oh, great. Or Donchin, I should say. But what is the future of computing? What we're looking at here is where's the limitation? Where can we make this system better? We can simplify it, and that actually is causing a great amount of efficiency to be put in today. We've written a few different types of connections. USB type communication is a very specific type of communication where it will read a serial number of zeros and ones on one wire, but it has minimized the number of zeros and ones required to identify the device. So what you have is it'll identify the device, transmit a piece of data, identify the device, transmit a piece of data.
This parallel communication is old-fashioned stuff, right?
This is something that's been around since the Apple II back in the 80s. This isn't anything new. When we're looking to make this more efficient, currently there's a great amount of research that's done into something called quantum computing. Okay? You know what that is?
Yeah, they throw quantum in front of a word to make it sound super smart.
Heck yeah, that's what we do in science.
Is that just like the algorithm stuff to speed up processing?
No. That's this principle. And it changes everything. It does. Imagine if instead of using a base 2 system,
Weird stuff.
or even a base 64. Okay? Right now, a hexadecimal system, I believe is 12. I don't remember what 16 is, but they're looking into a base 16 system. And just like what we showed earlier, it takes 10 digits to display like this 4-digit number in decimal. Okay? It'll take 3 digits to display this type of system in a base 64. 3 digits.
But it's not when you use the binary or binary system, you use the old form. That's how
Yep.
you get the 1 and 0.
Yeah,
How you can get the 3, 5, 6.
exactly. That's the problem this is the issue that we've run into. We don't know how to reliably get that information. Off and on is simple because it defies magnitude and noise. We can't find another really nice way of doing that, which is why quantum computing hasn't really been implemented. If we were able to implement a base 10 system, what you would see is that your computer overnight would become 4 to as many times as 400 times faster. Okay? Immediately. 5 to a lot, yes. Okay, so we don't have to change this hardware in order to speed your computer up. What we have to do is we have to change the way that the hardware interacts with numbers. We're still working on that as a society. This is something that there have been developments made in quantum computing, but realistically we don't know when those are actually going to hit the market. And when it hits the market, is it worth the cost savings? If it's 4 times faster, but it costs 18 times more to make, who wins? I could get 4 computers and take my 4 computers, plug them in parallel, have a supercomputer, and it's better. It is. That's how supercomputers work, is they actually do parallel communication. Yeah, that's how you build a supercomputer. Huh? A supercomputer? Yeah.
Yeah, let's build a super.
There are people who have built a Raspberry Pi supercomputer. We have one here. It's pretty awesome. You can do a whole lot with those because it uses parallel communication. Yeah, so this is one of the issues that we're running into. Quantum computing is great, but is this better than this? We don't know. That is the question. That is a question that scientists are still currently trying to figure out. We are, because I'm that smart. All right. I will be assigning you a reading assignment, a new quiz. This will be over AC systems. It will be due, actually both the reading assignment and the quiz will be over AC systems. I would advise doing the reading assignment before the quiz. I should have given you a reading assignment sooner on AC systems, but I didn't want to give you homework while you had a test. So most of you didn't even do the test until... Yeah, you're welcome.
Hey, I've been working on mine for 5,000 hours.
Mine was 7,000. Wait, no, mine was
Oof.
Mine was like 2 and 3. I spent like 12.
I opened it Wednesday.
All right, we will be doing a Pi Lab on Thursday. Yeah. So, bring your pies on Thursday. We'll be doing a lab then, okay? Nothing is due this week other than the test that was due, well, last night. Nothing else is due this week.